Okay, so guys, it's going to be kind of a crash course with all this because I got to go through, or I'm going to roll through at least the main points of the different types of segments you guys can see with circles. So we're not going to get into every little thing because there's just no time for it all before the FSA. So what we'll start with first is I'm going to deal with a couple of different segments or situations that arise if we're just strictly looking at tangent lines and how they're going to work with, interact with the circle. And then we'll do a couple with some chords and maybe a secant line at the end. All right, so to start with, oh my God, where's all my good markers? And a radius. Okay, so the first thing we'll talk about is if you have a tangent line going to a radius. That also will include a diameter, because if you got a diameter, right, half of that's a radius, so radii are going to be part of an actual diameter. If you have a tangent and a radius connected, so there would be my radius because that would be circle C. If I draw a tangent line to that, these will always make a right angle. Essentially meaning if you see a right angle, the Pythagorean theorem is going to pop up again. Just pretty much like any time we've seen right angles. If you get a right angle, I guarantee you're going to see some kind of Pythagorean theorem problem come from this. All right. Now, the way the problems are going to look, or very common ones, would be like they might have the triangle drawn that way, where they don't technically have a complete line, so I don't have a tangent line there, but I do have a portion of it connected to a radius. So as soon as you see a line connected to a radius, you can go ahead and throw a right angle in there. And what they might do is they might say like, okay, this length out here is, we'll make that 10. This length right there is going to be 15. And they'll say something like, find the length of the radius. Okay, meaning that, look, they're not necessarily going to have a variable on it. It's going to have you kind of recognize the fact that that's a radius. That angle is probably not going to be marked. You just have to remember that's a right angle. But then all of a sudden it just turns back into a Pythagorean theorem problem. They shouldn't really be more complex than that with this situation. At least the setup portion of it. So if I solve this out, I'd have x squared plus 10 squared equals 15 squared. What's 10 squared? About 15 squared. And then you subtract and you get 125, and then square root whatever that is would be your answer. Okay, so if you see, again, tangent drawn to a radius, or like if you see a tangent line drawn to a circle and they connect some kind of line to it, chances are it's going to be a right angle. Okay, so even if you don't know how to figure it out, you can at least take a chance of making it a right triangle and doing Pythagorean theorem and saying you know what's going on. Okay, next thing with the tangent line would be if you have two tangents. Okay, so if you got two tangents, what you're going to get is kind of a picture that looks like this. Okay, which again, these are extended out. They don't have to be there to make them actually lines. It's just a matter of these parts are portions of a tangent, which is why we consider it two tangents. Anytime you see a situation like this, they're going to be equal to each other. So if you've got multiple tangents going to the exact same circle, they're always going to be equal to each other. Okay, as long as they intersect at the same point. Right? I can't draw a tangent over here and assume it's going to be the same length. I just do it here because that is intersecting at the same point. So again, if I knew like that was 2x, right, and this was like x plus 5, I could just set those equal to each other. X to solve for the length of x, or the value of x. And if I need the length, I could plug it back in, right, and get 10 for both of them. Now, things that could happen is they can kind of combine the two. Like I could draw a radius here and here, and that would make two right triangles that are exactly the same as each other. That is a possibility of you seeing that. But you need to get down at least, in part, the two separate properties. So if you got two tangents that intersect at the same point, they're equal. If you got a tangent and drawn to a radius, it'll always make a right angle. Okay, good so far? All right. Next thing is going to be if you got two chords crossing. Okay, here, actually, let me redraw this. I don't want you to think that's going through the center. Let's draw it up there. Okay, so now again, like all the stuff I'm talking about today is just a matter of trying to figure out the length of segments here. Okay, so within this whole drawing right here, where I've got my two chords crossing, I'm left with, give me a letter. Give me another one. It would say H. And? X. Yeah, sure. Okay, so up there with my two chords crossed, they're going to intersect each other, and what's going to happen is they're going to form four segments. Okay? Now the way that this works is there's no like real magic trick behind this. It's just a matter of you have to remember that these are kind of broken up so that you are allowed to do the two parts that are broken up multiplied together have to equal each other. And it will always break up that way. Okay? So you take whatever this length is, multiply by whatever that one is. Okay, so that's on one chord. And then you set it equal to the same thing with the other chord. So the two parts that are broken up into, you multiply together, and that's going to set you equal to each other. So if I wanted to do that with variables, all right, let's say this is 3, that can be 4, that can be x in, I don't know. How long do you think that one is? If that's 4, how long is that? Maybe like 8? This, I don't know, 10 looks better. Even numbers. Yeah, I don't know. You look better than 10? Yeah. All right, so again, in this, you would be doing problems where it might be like, find the value of x. Okay, so if I wanted to find the value of it, again, like, so your mental process needs to be the same as with the angles. You got to kind of identify which situation you're working with. So this would be two chords. You'd have to remember, okay, if I got the two chords intersecting, the parts that are the chord is broken up into, if I multiply those together, I can set them equal to each other. So like this chord right here with the x on it is broken up into 3 and x. So if you multiply those together, it's going to be equal to the other two parts multiplied together. So this chord is broken up into 10 and 4. So that's how the setup would be. So 3x equals 40. So x is whatever 40 divided by 3 is. Okay? All right, now, in terms of just dealing with segment lengths here, there's only going to be one other situation that we'll run into, and that's going to be one where you've got this angle kind of formed on the outside. So if I wanted to classify these two segments, this would be like working with like two secants. It's not limited to two secants. It's more limited to wherever the vertex of the angle is in this case. So if the vertex of the angle is on the outside and I'm working with lengths of segments, I'm always going to set it up the way I'm going to write out here in a second. Each one of these secants, if I look at this top one, can you clearly see that this part of it is inside the circle? This part's on the outside. Yeah? All right, I'm going to label that as outside. Same thing goes down here, right? This is outside. This is on the exterior. That's on the interior. Now, in terms of like the actual equation that you set up, the part that's on the inside is not necessarily going to be part of the formula or the equation. But in order to make this complete, I do need to know how long the inside portion is. Because the way this works is it's going to be kind of similar to this one where you take the two parts that's broken up into and multiply them together. It's just when you do the ones on the outside, right, the angles on the outside, you take whatever's on the exterior, and you multiply it by the entire length. All right, same thing here. You got an entire length there. Yep, so this one goes exterior times the entire thing equals, again, exterior times the entire thing. Again, but it's going to be related to whichever secant you're working with. So if I put letters up here, E, all right, if I filled in this with the letters, let's say I looked at the top one, so the secant line that's on AC. The exterior portion would be BC. The entire thing would be AC. So when I say entire, I mean from where that angle starts to where it ends at the other side of the circle. Then the other one, so secant that's on EC, the exterior part would be that segment DC, and the whole thing would be EC. Now, what happens with this, and try your best to avoid this, is because of the way this gets set up. When you come to here, like your brain has to transfer a little bit as to not multiply these two together. Because what will happen is if you do a couple of problems like this, your instinct is to just take this part and multiply it together, but you need to make sure you're taking into account the entire length. So you have to like consciously make sure you're doing that. All right, so just for like an example here. All right, we'll do, this is 15, this could be 12, this can be 8? Sure, not too bad. What? And then this will be X. Okay, so now, the way I would go about setting this up again is I would have to kind of, in my head, recognize that this angle's on the outside. So if my angle's on the outside, I've got to set it up with the little equation that's over here. For me to use the equation that's over there, I need some kind of representation for the entire length. So if this part's 15 and that part's 8, what's 15 plus 8? Okay? And over here, I can't put a number on the entire length, but since I'm going to be solving for X, this is going to involve X, so when I set the equation up, I'll have something where I can just solve for X and be done with it. So to get the entire length, right, you've got to add them together. So my entire length is going to be whatever's on the inside plus whatever's on the outside. Okay, so now if I go back to over here, I've got whatever's on the outside times the entire thing on both sides of my equation. So on this side of the equation, like if I look at this left-hand side, the outside part is 12. The entire thing is X plus 12. If I look at the other one, the outside portion is 15, and the entire thing is 23. So now you're down to where you can just use some pretty straightforward algebra and solve it out. If I distribute the 12 here, that gives you 12x plus 144. And then what's 15 times 23? What's 15 times 20? We'll do it that way. There you go, 345. Okay. What's 345 minus 144? And then whatever the heck that divides to is going to be whatever the answer is. So again, like I said, the biggest mistake here would be someone doing 8 times 15 equals 12 times x because of the way we do that problem. All right, so that's like all that stuff I just went through. Those are all the different situations you're really going to be dealing with, like segments and circles. There's a couple other things that could pop up with like a radius going through a chord at like 90-degree angles and stuff, and I might eventually get to that, but we're not necessarily going to talk about it right now. The only other thing I want to talk about today is the equation of circle in the coordinate plane. Meaning, I'm going to be looking at a circle. It's going to have coordinates for center point. I can count radii, so on. There is a general, like a standard form for this equation that you guys have to know. You've got to be able to use the equation to pull a center and a radius out of it. And you also have to do that in the reverse, meaning that I might give you something graphed out where you can identify the center, identify the radius, and then you come up with an equation with it. Now keep in mind, right, there's nothing, like when I do this, you're not solving for anything, you're writing an equation. Just like if you write the equation of a line, you can write y equals 2x plus 3, and that's it. That would be the equation of a line. There's nothing to solve there. You can utilize it for other things, it's just there's nothing really to solve. Now the way the equation of a circle looks, it looks like that, which is, it's basically Pythagorean theorem, because by definition a radius is a set distance from a center point. So if I go from the center to any point on the circle, it's going to give me the exact same length. That's simply distance formula, which is Pythagorean theorem. Okay, now, yeah. It's the same as the quarterly ones, which is very limited. There isn't much on there at all. I don't remember. I have to look. I can check. It's like midpoint. It might have. It has like I think a volume formula on there. I don't think it has distance or anything because you're supposed to remember distance by Pythagorean theorem. So all that stuff's in there like that. Okay, now the letters up here. Okay, X and Y. Every single time they're in there. Right? Because, again, going back to if I looked at a line, you don't have to write this part down right that I'm doing right here. If I write the equation for a line, I get things that look like y equals negative 3x plus 10. Right? And I could graph that out. Okay? So just like with the line where you have to have x and y and they're at least one of the variables, same thing goes here. This is going to be a number, that's going to be a number, and so is that. The x and y stay x and y, the other three places you put numbers. The h and k, that's your center point. So again, this is in the coordinate plane, so you're going to have variables for those. If you got a 0 for one of them, you can just drop it out of there. Like if this number was a 0, I wouldn't necessarily write x minus 0. You would just drop the 0 part and leave it as x squared, which just looks nicer. And then r, that's the length of the radius. Now, since we're dealing with distance formula, the actual equation has r squared in it. So that's how Pythagorean theorem works, right? A squared plus b squared equals c squared. So the r has to be squared in the actual equation, but the actual radius length is the one without the squared. Okay? So if I wrote an equation that looked like that, I could ask you to pull the center point out. I could ask you what is the center, and I can ask you what's the radius, and you should be able to pull those out. Okay? Now, the one place people get messed up is if you look, right, since the equation's dealing with distance, you have negatives in here as a base. But if you have a negative h, your actual center is the positive, because all you look at is this number right here. You don't look at the sign that's in front of it. If the sign changes, though, from a negative to a positive, that would mean that your h's and k's would be negatives. Okay, so like if I looked here, that's my h, that's k, this number here is r squared. So my center point here would be 2, 1. And then I know since r squared is 9, if I take the square root of 9, that gives me what? 3. So my radius is 3. Now, the things you can do with that, the only thing you might have to do with that is you might have to graph that out. X and Y are just X and Y, man. You're writing an equation. When you have equations, you have to have X's and Y's in there because they work as like a function where you plug numbers in to get specific answers. So you have to leave X and Y in there as just simply X and Y. Okay? So there's nothing else you do with it. If you plug numbers into everywhere, all it's going to do is give you a number. You can't do anything with it. So what equations do, like see with a line you have an X and Y because I want to be able to plug a number in here and get an answer for the other one. Okay? Now look, if you had to graph that out, okay, the way this would have to work, and I can't imagine, if this is on the FSA at all, the way this would have to work is you would have to be able to plot where your center is and maybe stretch a circle out to hit a specific radius. If you have to do this by hand, which I'd probably give you like one of these to do today. They're not that hard, and guys, it's just a sketch. I'm not asking you to get a compass out and construct a circle or anything like that. The things that I would be checking if this was some kind of test is I would want to see that center point plotted correctly. So I would go 2 over on the X, 1 up on the Y. Here's my center point. 2, 3. Okay, and then the other thing I would want to see is I would want to see points from that center that are exactly 3 spaces away. Now, you can do it with maybe a Pythagorean theorem or something if you wanted to make it complex. But if it's on the coordinate plane, I can count up and down and left and right in exact numbers, meaning that if I go from here and I go up 1, 2, 3 spaces, that point has to be on a circle because that right there is 1 radius length away. So I know that that point right here is on the circle. I can also do it in this direction. I can go 1, 2, 3. That point's on the circle. And I can go 1, 2, 3 down. That's on the circle. And then 1, 2, 3 over. Those are all on the circle. Obviously, this scales me off some because I don't have it like perfectly, spaced out. But if you did this on graph paper, you would see that all those points should be the same distance from that center. Then for your sketch, guys, the only thing I really ask you to do, if you were doing this by hand, is make sure it kind of resembles a circle. I'm not going to draw a perfect one. Unless you're amazing at that, you're not going to draw a perfect one unless you have a compass. Okay? The only thing I really don't want to see is I don't want to see that. You know what a circle looks like. They don't have flat edges on them. Don't do that. Okay? Give me at least some kind of curve to it. It doesn't matter if it looks poopy or not. Okay? So long as it kind of looks like a circle, and the center points are there, and these 4 points are there, that would be perfect. So in essence, when you're graphing these out, you got to plot 5 points. You got to plot the center, and then you got to plot one above, a below, and to the left and right that are a radius length away, and then just connect them.